So the last testing that we have to do has to do with linear regression. It doesn't show up that often on the AP test. I can't remember last time it showed up. Maybe 3 years ago it showed up in a little way. So that's why, like, when you take your inference test when we come back from break, Chapter 13 is not on there. Because it doesn't show up a ton. A lot of it stems from Chapter 5. So it's just like a good review of Chapter 5. So we talked about this last week. If we estimate our least squares regression line, we use A and B. If we're looking at the true regression line, we use alpha and beta. Okay, not the alpha and beta from Chapter 10. Like, alpha stands for the y-intercept, beta is the slope. Your estimated standard deviation, we use S sub E. Your true standard deviation, we use sigma. So, if I had this one example, it's a weird example, but it works. When people have colds, common wisdom says to avoid dairy products since they produce extra mucus. However, this claim was challenged by researchers in Australia in 1990. They infected volunteers with a cold virus and assigned them at random to drink different amount of milk. Meanwhile, all used tissues were weighted to measure nasal mucus secretions. Yeah, it's a weird example. But the point is, in this, so they had the glasses of milk and how much mucus they had. The slope here is 0.0567. So let's interpret this with our Chapter 5 stuff. So for each additional glass of milk consumed, we predict the amount of mucus to increase by 0.0567 ounces. So, at first glance, you think there's a positive association between the milk consumption and mucus secretion, since the sample slope is 0.0567, which is greater than 0. Why might it be possible that there's no association between the variables? What's happening with this slope? It's positive, but think about the number. It's very, very tiny, right, close to 0. Remember what happens when you have a slope of 0? Yeah, there's no correlation. It's like a flat, horizontal line, right? So the slope is not very steep and close to 0. And usually when we say there's a 0 slope, that means there's no correlation. Think about the concept we've been talking about all year, right? You have sampling variability. Our next sample could have a negative slope. Okay? Because it's so close to 0. I mean, it's positive, that's great, but it's not like the best positive number ever. So if there's no association between milk consumption and mucus secretion, what would we expect our slope beta to be for the true population regression line? We sort of already said it. It should equal 0. So the regression line would be horizontal. Right? No relationship, no correlation. If there was a positive linear relationship between milk consumption and the mucus, we should have beta being greater than 0. Because then that way our slope is positive. So we're going to end up doing testing based on these kind of things. Is it 0? Is it not 0? So the mean value of B is beta. So that's the sampling distribution of B. Our slope from our sample or our point estimate is centered at our true population slope. So we're going to do a write-up when it comes with, is there a linear association, is there not? Is the slope 0, is it not 0? We don't necessarily look for positive, negative. So on the next page, this is kind of how you do your hypothesis test. We're going to do a hypothesis test today. We'll do confidence interval tomorrow. So you don't need the calculator really at all. We're not going to throw, there is a linear regression test in the calculator, but that only really works if you have data. And a lot of times, to save time, we're not going to give you data. We're just going to give you the Minitab output, especially because this doesn't show up very often on the AP test. So our conditions are very similar to what we've been doing. Data is from a random sample. Now, condition 2, we usually look for, is it normal? Is it a normal distribution? Here, we're looking for no pattern in the residual plot. Do you guys remember doing residual plots in Chapter 5? We always look for if there was a pattern or not. So that's your condition 2. If there's no pattern, so then our linear model may be appropriate. Most of the time, I'm not going to make you do a residual plot on your own. They'll give you a picture. You won't have to do it. Because in order to do that, you need data. And half the time, they won't give you the data. We're going to do a linear regression t-test today. There is no such thing as a z-test. And our parameter that we're looking at is the slope. So you have to, that's why we went through and had you interpret things in the regression review worksheet. Because we're going to have to define the slope. Your testing is that you're assuming there's no linear relationship. Beta is 0. You're trying to prove there is a linear relationship, that beta is not 0. Again, we very rarely go positive, negative. It's usually just, is there a relationship, is there not a relationship? Always provide these with context. Okay? Just like we did in Chapter 12 with the independent. Give me the 2 variables. Your test statistic will be B, which is the slope of your sample, minus beta, which is the slope of the, this one's usually 0. And then S sub B, which I'll show you where that is. And degrees of freedom is n minus 2 instead of n minus 1. I like to remember it's n minus 2 because there's 2 variables that you're looking at. S sub B is the standard deviation of the slope. So S sub B describes how much we would expect the sample slopes to differ from sample to sample. So SB and SE are different. SB is the standard deviation of all the slopes. SE is the standard deviation of all the data. Right here. Again, here's the test in your calculator, but we're really not going to use it. And then our conclusion is, since our p-value is greater than or less than our significant level, there either appears to be a useful linear relationship or not. Just depends. Now, like I said, a lot of times they'll give you data. They'll give you a Minitab output instead of the actual numbers. So this is a random sample of 18 individuals. We're looking at the percentage of fat versus their age. So let's go through and remember what everything is that we're going to need to know. First thing you got to remember is these 2 numbers, right? This is the y-intercept. This is your slope. Now, S sub B, remember that's the standard deviation of your slopes. That's this 0.1056. This is SB. This S over here is SE, the standard deviation of the residuals. This coefficient for the constant, you do not need to know that. When we do our testing, the T and the P are actually already given on here. Sometimes they'll get rid of it. This is going to be our T value for our testing, and this right here, the 0, is our P value. You don't need to know that. You don't need to know that. R squared is R squared. You don't need R squared adjusted. For the variance, they may ask you to find SE and R squared by hand if they only give you this section. 16, this is your degrees of freedom, because n is 18. Remember, the total is really n minus 1. This is your SS residual, SS total. You don't need to know MS, F, or P. That's for something we don't do in this class. And I threw on the residual plot there. So for this question, if I want to know the regression equation, all I really need is slope and y-intercept. Now, if you want to make it easier on your life, you can write your regression equation like this. Predicted percent fat equals 3.221 plus 0.5480 times the age. I like to do this at this point because you guys have seen this stuff enough. Instead of using x and y hat, because then you don't have to define x and y hat. Especially if the words are relatively short, like if it's not a long thing. So that's our regression equation. So let's interpret the slope and y-intercept. So we're looking at age and your predicted percent body fat. So for the slope, of course on the other page, our slope was 0.5480. So for every year increase in age, we predict the percent body fat to increase 0.5480%. And it was already given in percentage, so you don't need to convert it. Y-intercept here was 0.3221. So remember, that's when x is 0. So when your age is 0. A newborn, you could put in parentheses 0 years of age. We predict to have 3.221% body fat, which is so not true. You ever heard of baby fat? So the first 6 problems are all kind of review. Well, 4 and 5. 6 is new. So interpret R squared. So R squared was 62.7. So 62.7% of the variability in the percent body fat can be explained by the linear relationship between age and percent body fat. Again, this is written on that homework, the regression review, in case you forget it. Interpret the value S sub E. Again, SE is this 5.754. So the value 5.754 measures a typical amount of variability in the vertical distances from percent body fat to the least squares regression line. Now, the new one is SB. How do we interpret SB? So it's the standard deviation of the slopes. So again, it's right here. So it's next to the actual slope. So I think slope and then standard deviation of slope. So 0.1056. Here's how I like to interpret it. There's like this fancy way to do it. I just think of what's in bold here. How much we expect our sample slopes to vary from sample to sample. So if we all went out and took different samples, we would all get slightly different slopes. This is the standard deviation of all of our samples. So it's how much we expect our sample slopes to vary from sample to sample. Again, you want sort of a small number, right? If the variability is small, that means we all got around the same slope. If the variability is large, that means some of you may have gotten positive, negative, some of you could have gotten 0. So, question 7 is the big guy. This is our actual hypothesis test. Is the linear model appropriate for this situation? Before, in chapter 5, we would just look at the residual plot. Now that we have all the data, we can actually do a hypothesis test. So, for our conditions, and again, it doesn't show up a ton on the AP test, which is why we're not doing a ton of it. I think on your homework you maybe have 2 examples. But you still kind of have to know what it is. Data is from a random sample. Now, if they don't give you the residual plot, which I did, sometimes they'll say, assume the conditions have been met. You can just skip 1 and 2. But you still have to do 3 and 4. You still got to name the test and tell me what the slope is. But you can skip actual 1 and 2. So I think on your homework you can. So here I do have a residual plot. Does there look like there's a pattern? Or does everything look scattered? I mean, it's kind of like a... But we'll say no pattern. There is no apparent pattern in the residual plot. Therefore, our linear model may be appropriate. Oops. So we're going to do a linear regression t-test. And our slope, so you're looking for the true whatever. So here it's the true change in percent body fat for each increase in year. Okay, think about number 4 as you almost interpreting the slope. Okay, so you're testing. Again, there's no picture that you need to draw. It's just either the slope is 0 or not 0. But you need to put those in context. So our null hypothesis is that beta is 0. There is no useful linear relationship between percent body fat and age. Our alternate is that it's not 0. Again, we're not really caring. The question not asking it, is it positive, negative, or 0? So there is a useful linear relationship between percent body fat and age. So when we do our test statistic, the only things you have to list, there's like 5 of them. So for our test statistic, you want to name, you got to give me the slope. The slope of this line was 0.5480. You got to give me standard deviation of the slope, which is, where'd it go? 0.1056. That's S sub B, sorry. N was 18, so degrees of freedom would be 16. Our alpha here is 0.01. So we're actually doing a t-test. So really, if you were to use your formula sheet, we would be using the t-distribution to find our p-value. But I'll show you what we do. So you find your test statistic. So it's your slope, 0.5480, minus 0, divided by your standard deviation. So you don't have to plug anything into the calculator. So I get 5.19. Now, if you look at the mini tab, it should match what our t-value is, 5.19. I still need to see the work. Then that's your p-value. So a t-value of 5.19 gives us a p-value of 0 with 16 degrees of freedom. And really, all you're doing is dividing the slope divided by the standard deviation. So then your conclusion, we're less than, so we're going to reject our null hypothesis, so we're going to go with there is a linear relationship. Since our p-value is less than our alpha, we have evidence to reject the claim that there is no useful linear relationship between percent body fat and age. It appears the linear model is appropriate for this situation. Oops, that's not a question. That's a period. Okay. Questions at all? So again, that's your last hypothesis test. Tomorrow we're going to do confidence intervals, which will just give us an idea of what exactly we think the slope is going to be. And then we're done.